So just looking down the road, probably Tuesday. I don't know. And by the way, might as well just quickly talk about the lockdown drill. In the past, now we're doing it a little differently. And I don't know how much your Bearcat time teachers told you, but it seems to often fall during second block. But they're not going to tell us this year. They want it to be more unannounced. So it's next week, but I don't know when. I'm gonna do some checking to make sure it's not on Tuesday. If it's gonna be Tuesday during second block, then I don't want to be doing the quiz. So anyway, that's the number one reason I'm thinking about it, mentioned to you guys. But it may not be during second block. It may not be on Tuesday. They haven't told us. I'm not sure they're going to tell us because I think they want it to be unannounced. And it's supposed they're going to make it more realistic. It's supposed. I don't know how realistic. I don't know. Well, that's going to be a shock. Yeah, I don't know. I don't know. All they've told us is someone in the building that maybe looks like they don't belong, kind of thing. And I think they want to test to see how long it takes, how long this person can be in the building before someone reports.
That's hard to tell though.
Well,
we have some.
Right. No, I know.
It's hi to everyone.
Right.
I'll probably be saying hi to. I'll probably talk.
You're probably talking.
Like, hey, how's it going?
Welcome to the party house.
My name is. They don't know.
Yeah, I don't know.
I'm talking for like an hour.
Well, that's good of you to give yourself up for the rest.
Yeah.
But if it should happen during this class, I mean, but one of the things that they've emphasized, like in the videos, that's a little bit of a change. I mean, if you go back 3 years ago when you guys, most of you were freshmen, you know, it was pretty much lockdown, meant in your room, hide, get in the corner, whatever. And now you notice over the years they kind of start changing that, where fight back a little bit, get out is kind of the first line of defense. So if they would come over the intercom, you know, and say, there's an intruder in the building near the cafeteria or in the concourse, you know, from this room we would probably hustle out and go outside.
I'd be sprinting.
And so, you know, so if it's in the 400, 600 hallway, yeah, we'd probably stay put. So if that would happen in class, that would be what we would want to do. They want it to be more realistic. I know last year I kind of got not reprimanded, it's too strong of a word, but it was between, I think it was between a passing period and like between 2A, 2B. There's like a skinny. So most people were in class, but there were some students in the hallway because of the passing period. Some of my students, well, I'm trying to think, was it 2? Maybe it was like 1, because it seems like I had a skinny. It might have been a skinny. But anyway, I was out in the hall and I had some of my students I could see cleared out the end of the hall, and I was shooing them to come down, you know, and they were saying, no, they should have went into the nearest room, you know, and kids were just kind of walking like normal to the room. You know, we should have been more urgent, you know, whatever. So anyway, but so that's coming. But I mentioned it just because the quiz is planned for Tuesday. If I would find out that that's when they're going to be lockdown and it's going to be here, maybe they will tell me, I don't know, then we may switch that. But for now, that's what we're going to do, okay? So we're in the middle of section 3 right now. So just some quick things. 2.1 is when we learned the derivative the long way, the definition of the derivative. Of course, I've got it up on the board. That's the version we would use now. We did f prime of a, f prime of x. Same thing. If you want to find f prime at a certain point, if you want to find f prime of 2, you just put a 2 in for this x, would be a 2 in for that x, would be a 2 in for that x. Or if you just want to find f prime of x, then, you know, you just leave the x in there and do it like we've done a few here lately. So we have that. And then we learned the shortcut, the power rule, right? The power rule now. We shouldn't call it shortcut. I guess we should call it the power rule for doing derivatives. So there'll be a little bit of that. Not a lot of that. We'll be doing a lot more of that in Chapter 3. But some fairly simple ones, kind of like what was on your homework yesterday. Okay, doing some of those. So there'll be a little bit of that. 2.1, that long way, you're probably going to have that at least a couple times. And there's going to be a calculator part and a no calculator part, and it can be on either part. I mean, the calculator doesn't really help you there, right, on that. You still pretty much have to show your work and work it out. So the calculator doesn't really help. And even if it's one you know the answer because you know the shortcut, you know, you still got to write it out. You've got to show the work. practice that, and you want to make sure you do that. Okay? And so the next thing here, then in 2.3, this is what will be a big part of it. That's what we'll work a lot on today and tomorrow. A lot of work on section 2.3, this idea of limits. Now, you don't have to necessarily jot all this down right now, but I mean, you can. We'll be going over it again. But basically, we've done limits. You had the worksheet where we did them algebraically, right? We can do limits algebraically. Now, the first thing you actually do is substitution. So I really don't have these written in any kind of order, but really substitution's always what you should try. If you're doing the limit as x approaches 2, you should plug in a 2 and see what's happening to that function at 2. It's possible you plug in a 2 and just get a number, like I wrote over here, right? If I want to do the limit of x plus 3 as x approaches 2, I just plug in a 2, I get 5, and I'm done. That's my answer. That's what the outputs are approaching as x gets close to 2. Okay? Actually, the output is 5. As we learned on the video, though, the diner might have burned down. There might not be an output there. It doesn't matter. There's still a limit. It's what the cars are coming close to, but it might be the output. So we try it. We plug in a 2. We get a number, fine. But if we don't get a number, most of the time, and there's a blue check mark here, most of the time you're going to get that. You're going to get 0 divided by 0. In most of the problems we do. Most of the problems that are interesting. So basically, and that has a name, by the way, it's called indeterminate, which just means with that information alone, you can't determine what's going to happen. You can't determine if there's going to be a limit or not, or what the answer is going to be. You've got to keep going. And so that's where the algebra would come in. Maybe you factor and cancel. Maybe you get a common denominator and cancel. Maybe you do a conjugate and cancel. The canceling is the key part, because something will cancel, and then you can do substitution. Then you can plug in and get an answer. And then over here, number 3 on the right-hand side, the other thing that could happen when you do substitution, I mentioned this yesterday briefly. You could substitute in and get like 6 divided by 0 or 2 divided by 0 or something like that. That's different than 0 divided by 0. If you get 6 divided by 0 or 2 divided by 0, that does not exist. What it is it's a vertical asymptote in the graph is what's going on. And the cars aren't going to meet because you got these asymptotes, you got these graphs just going up, like the tangent graph, for example. It just goes up, 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 and down, 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 and down. The cars would never meet, and so we say the limit does not exist. Okay. So somebody asked that, yesterday. How do you tell if the limit does not exist? Well, if you're doing algebra, if you're just doing substitution, that would be a way to tell. If you get 6 over 0 or 2 over 0, right? Now, if you're just looking at a graph, we'll skip number 2 here. If you're just looking at a graph, how do you tell if the limit does not exist? If the cars don't meet. If the cars don't meet. So if you had a graph with the parabolas going like that, right, or parabolas, the asymptote, you had to say the cars would meet. If you have a piecewise graph, right, you had some of those in the book, you have a piecewise graph, and the cars don't meet, the limit does not exist, right? That's what happens when the limit does not exist. The cars don't meet, right? But of course, if you're not looking at a graph, cars meeting doesn't have much meaning, right? So that's what it would look like in an equation. You get 6 over 0, 2 over 0, something like that. That's when you say it does not exist. But 0 over 0, you don't say it does not exist. 0 over 0 is special. You keep going. You do one of these things. Today we're going to talk about tables on a calculator, how we can see limits that. Okay? All right. And then what we'll get into a little bit today is a little bit in 2.4, and that's chart stuff with equations. Now, we've already talked about that a little bit, all that chart stuff about local max min, increasing, decreasing, stationary points, when the derivative is 0. Now that we have this shortcut, the power rule, we can do, if we want to ask when function f is increasing, well, that's when f prime is positive. Now, when you look at a graph, it's easy to tell when f prime is positive. It's when it's above the x-axis. But how do you tell when an equation is positive? That's what we're going to work on today. And, of course, the key is you find where f prime is 0. You find where f prime is 0, so you'll solve an equation. So we're going to work on that today, see what chart stuff looks like when you have equations. Okay? Which, of course, is a result of what we've learned here. Okay? With our power rule and stuff. Okay? go to the homework. So let's go to your worksheet first. No, I take it back. Let's go to the book problems. Those are easy, right? Those are easy. So, talk about the cars meeting, not meeting, function values, that kind of stuff. So on 13 through, so there's going to be some of this. So you can expect a problem where you have piecewise function like this, and I ask you some limit problems about it. Yes, ma'am.
So like on -3 and on 2 and on 4, where it has just the dot, you know what I'm saying? What purpose does that serve?
The dot? Nothing. Well, that's not true. That's not true. What purpose does the dot, what is the dot?
The actual.
It's the output of the function at that point. Now, could this be filled in and have a dot here? It wouldn't be a function, right? Fail the vertical line test. You can't have two outputs for any one input, right? So all that is saying that that is the output of this function at -3. Yeah, that's all it is. But what it does in these problems is it serves the purpose of really emphasizing to us that limit and the output are related, but they're not the same, right? Because the limit, and that's probably one of the questions, the limit as x approaches -3 is not one of the questions. Yeah, it is, number 14. The limit as x approaches -3 is what? -1. That's where the cars are meeting. The diner is burned down. It is moved to a new place, right? I guess you might say with this point. But that doesn't matter. The cars are going to meet right there. That's what a limit is. So the limit is -1. But if I would have asked you what is f of -3, you would have said +1. F of -3 is +1. The limit is -1. That's where the cars meet. Okay, limit as x approaches 0. What'd you have? 2, right? Which also happens to be f of 0, right? But the cars meet right there at 2. 15, as x approaches -1. Doesn't exist. The cars don't meet. As x approaches, number 16, x approaches 2 from the left. 1. From the left, the car on the left would be approaching 1. As x approaches 2 from the right. Also 1. So therefore, 18 says what's the limit as x approaches 2? 1. In other words, what those three problems were showing is that there's a limit from the left, there's a limit from the right. If those two limits are the same, then that's the limit, right? Which is like the cars meeting, right? Here, the limit on the left would, well, they probably ask that, don't they, later on. What's the limit as x approaches -2 from the left? 0. Easy one, right? 0. What is the limit as x approaches 1 from the right?
0.
From the right, x approaches 1, the y value is approaching 0. The y value isn't 0, but it's approaching 0 because there's a hole there, but that's the limit. -4 from the right. -2. What would that you say if it asked what's the limit as x approaches -4? Just not from the left to right, just as x approaches -4. I probably would not ask you that because it's kind of a trick. You would say does not exist because you have no information from the other side. You have to be able to see both cars, right? So I probably would not ask you. It's kind of a trick question, but it points out the limit, the actual limit as x approaches 2 or 3 or 4, you have to be able to see what the function's doing from both sides, okay? That's why they only ask from the right on that one. And it would be kind of a trick question to ask you that, but you've got to see both sides. So I would say does not exist there. All right, x approaches 4 from the left. -1, right? X approaches 4 from the left. We don't care about that dot. The car is approaching -1. X approaches 3. Oh, now this changes. I don't know if you noticed that. You notice it said f prime? Okay, so now what are the outputs of f prime? Slopes of f. Now remember, what we said is the limit is what are the outputs approaching. So now you say, well, we don't have an f prime graph, but we can think to ourselves what the slopes are, right? Those would be the outputs of f prime. So they want to know what is the limit of f prime as x approaches 3. So as x approaches 3, what's the slopes right here where my fingers are? -1. What's slopes? So as x approaches 3, the slopes seem to be approaching, not only approaching, they are -1, right? If you actually were going to graph the f prime graph, you'd have a horizontal line at -1. So the cars would be meeting right at -1. So the answer there would be -1. So make sure you notice that as you're going along. -1 from the right, but you're doing f prime. So the slopes are 0, 0, 0, 0, 0. So they're approaching 0, not only approaching, but they are. Okay? F prime of -1 from the left, 1, 1, 1, 1. Different slope. So then, what's the limit of f prime? Oh, they didn't ask. So the limit is x approaches f prime, or is x approaches -1, would be, does not exist, right? Because you'd have -1 slopes on this side, or no, not -1, +1 slopes on this side, 0 slopes on this side. But they didn't ask that one. X approaches -3, f prime, 1, because the slopes are 1 here, slopes are 1 here. So as x is approaching -3, the slopes stay constant. They're 1. All right. So then we jump to 39 through 42, right? 39 through 42. So let's take a look at that scenario. Now, it's very likely that I could give you something like this. We've talked about in our first quiz, our very first quiz, we did piecewise functions. So you might, and this would most likely be on the no calculator part. So if you want to use a graph of this, you could. This says x is less than 2, and then it says x is greater than or equal to 2. So if you want to do a graph of this, that could be helpful. If I was to ask you a question like this, I'd probably put an XY axis there and say, you know, a graph may be helpful. Use it if you want. Now, I might also say draw a graph of this, but we already quizzed on that. You know, we did that on our first quiz, so probably not going to make you draw the graph. But if you think a graph would be useful in doing your limit, because it'd make it easy, just like the last problem we did, if you got a graph, they're pretty easy. Okay, so if you want to do a graph and you think you can do that, then I would say go ahead. This would be upside down parabola, shifted up 3. So you could do that. You would know if you put a 0 in, you're going to get 3, and you just plot a few points. Now this is when x is less than 2, so I could just go over, put a 1 in here, I get 3 minus a half. So that'd be a 2.5. And then put a 2 in there, that'd be 4 times a half is 2, 3 minus 2 is 1. So it looks like it would kind of come down like so, across there somewhere, but I don't care. I guess I don't care about the rest of that, do I? I only care about it when x is less than 2. Okay, and then there'd be this other part of it, which would be this way. Okay, -2 would come down here at 1, and then cross, do something like that. And that says less than 2, so this would actually be an open circle here at 2, 1, something like that, right? So I'm just plotting a few points. 3x minus 5, so that would be down here, y-intercept of -5. It would go up 3 and over 1. It would go up 1, 2, 3, and over 1. So it would cross right through there, wouldn't it? And then it would go and keep going, right? Like so. So from 2 on, and it would fill in. So that's interesting. So what we have, so that's something really important just happened right there. Because if you have a break, what happens with limits? It does not exist, right? So with a piecewise function, when you have a piecewise function, what you're really interested in is there a break? Well, if there's going to be a break, now pretend I haven't even done that graph. Just look at the piecewise function. If there's going to be a break, where's it got to happen? When x is 2, right? It's got to happen when x is 2. Because when x is less than 2, you got a parabola. You know that never has any breaks in it. And when x is greater than or equal to 2, you got a line. So the only question is when the parabola stops and the line starts, do they meet, right? Does the one end at the same place the other one takes off? Well, you can just do that by plugging a 2 in, right? Even though you know that this doesn't include 2, plug a 2 into it to see. And of course, that gives you 1, and you put a 2 in here, you also get 1. So even without the graph, I could have known if there's a break or not by just taking a 2 and plugging it into each of these. And since I got the same value, I know that one stopped and the other started from the very same place. But anyway, now that I've graphed it, it becomes pretty easy to answer the questions. So 39, the limit as x approaches 3. See? Now, do I need to know? No, it wouldn't be 1, would it? Be 4, wouldn't it? Now, again, do I need the graph for that? Not really, right? Because when x approaches 3, where on this graph do I know I am? I'm on the line. Well, when you're on a line, doesn't the limit exist everywhere? Wouldn't the cars meet everywhere? Right? Yeah. So you know, so if you really understand what's going on, if I say the limit as x approaches 3, I really would not have had to graph this. I could have just said, oh yeah, when I'm at 3, when I'm at x equals 3, I'm on the line. And the cars would meet everywhere. So all I got to do is plug in a 3 and that'll be my answer. So 9 minus 5 is 4 and I'd be done. So you really wouldn't need the graph. But if you want it and to look at it visually to see it, it can sure help. 40 says limit as x approaches 0. Well, at 0, I know I'm on the parabola, right? When x is less than 2. So when I'm at 0, I know I'm on the parabola. I know the cars would meet everywhere when I'm on the parabola. So I just put in a 0. I'm going to get 3. Okay, the cars would be meeting right up there at 3. But if you want the graph, it can help. Then the one that's really the most interesting is number 41. That's the one we care about. When you get a piecewise function, where a limit question will be interesting is at 2. Because that's where one graph stops and the other one starts. And you might get this break like we had in the last set of exercise. Okay? So what I would do on this one is simply what we've already done. I would plug in a 2 into this one. See where that car's headed? Right? Isn't that what you would be doing? By plugging a 2 into this, you'd be seeing where the car on the left is headed as it gets towards 2. By plugging a 2 into this, you'd see where the car on the right is headed. Make sense? So you put a 2 in here, you get 1. Put a 2 in here, you get 1. They're meeting at 1. There's your limit. So you could have done it without the graph by just knowing that. But looking at the graph, it's nice as well. Probably depends on how good you think you are at drawing a graph. Right? If you think you would screw up the graph, you might not want to do that. All right, x approaches 1. Again, x approaches 1, we're on the parabola. So that'd be here. So you plug a 1 into there, 3 minus a half is 2.5, and there's your answer. Okay? All right, so there you go. How do we do? 100%? Sort of, kind of? All right. So let's go to the worksheet. Good news, bad news, right? The good news, get that out of the way, now we'll do the bad. All right, so on the little thing I said for review, so we talked about limits, and we said, okay, be able to do limits with graphs. That should be probably the easy part, right? Do the cars meet? Where do they meet? Where are they headed? Limit from the left, limit from the right, that kind of stuff. Okay? We get into ones where, and there'll be some, and it's not a huge amount. I mean, there's a lot of different things here, but there's going to be some, like this worksheet, where you're going to have to do some algebra. You always start, and these would be the no calculator ones. Probably this would be on a no calculator piece here too, the graphs. I just give you the graph or a piecewise function, and you could sketch a graph if you want. Okay? And then these would probably be in the no calculator section as well, these algebra ones. Okay? So, you start by doing substitution, and then you check, am I getting 0 over 0? Then I try one of these techniques. Or am I getting 6 over 0, something like that, then I just say does not exist. Okay? All right, so starting here, I just want to quickly run through these. So we're going to, well, we first put in a 2, we get 0 over 0. Right? Don't forget that substitution piece. So now we get x minus 2, x minus 5, x plus 2, x minus 2. Right? Cancel, cancel. Now we can plug in our 2, we get negative 3 over 4, and we're done. Right? Okay, move over to this one, plug in a negative 1, and again, you get,
negative 2 over 0.
Excuse me, negative 1 would be 1, minus 1 is 0, minus 2. Yeah, you get negative 2 over 0, don't you? Which right away you can just say does not exist. Now, what if you factored that? Because it does factor, right? So if you factored this, and did that, and then plugged in your negative 1, now you get negative 3.
I think you switched those around.
What did I do wrong?
Minus 1.
Plus 2, minus 1. Be helpful if I could factor. Okay, so now we still got this. There we go. I was going to say, that's not working like I want. So put a negative 1 in. So you get negative 1 plus 2 is
1 over 0.
1 over 0. There we go. Which is still does not exist. So either way, should have substituted in first, but sometimes we get so caught up in the factoring that we do the factoring part first. That won't hurt you if you do that. It won't hurt you. So it turns out the x minus 1s are the ones that cancel. So if this would have been the limit as x approaches 1, then we'd have been in business. Because when we plug a 1 in here, we get 0 over 0. Those would have canceled, and then we'd have got 3 over 2, and we'd have got 3 halves. What this one is, what happens here is, notice the bottom is 0 at 2 different places, right? It's 0 at 1 and at negative 1. Well, what you have is, at 1, you've got a hole in the graph. And at negative 1, you've got this asymptote situation happening. So it's 2 places it's undefined. One of them is 1, one of them is negative 1. But it's 2 different types of undefined. The one at 1, you get 0, 0 is a hole. The other one is this. So we happen to ask at negative 1, well, the cars wouldn't meet, right? The cars would not meet. If you had a graph of this, it would look something like this. The cars don't meet. So it does not exist. But if we'd asked this same function and we'd asked at 1, then we'd have got an answer, right? Like 3 over 2 or whatever.
What
Yeah.
if it's approaching 0? Like, what if 0 is the answer?
That's okay.
Then how would you, like...
I mean, if you get like 0, what you would get is like 0 over 3.
Okay.
Yeah, if you plug in a number and get, yeah, that's a great question. So what are the options with getting zeros? You could get 0 over 0, which means keep going, something's going to happen. If you get a number over 0, that does not exist. If you get 0 over 4, that's just 0. Yeah, and then that means, that'd be like right here, right? That's like right here. The cars are meeting at 0. Yeah, because 0 on top's fine as long as you have another number on the bottom. Yeah, then the answer is just 0. I'm glad you said that, because sometimes people get so caught up in thinking that does not exist or something. No, 0 over 4 is 0. Okay, and that's a perfectly valid answer. Okay, we keep going. So you can see there's more of an emphasis on the factoring parts. There's probably going to be more of those than the other ones, right? We're pretty good at that. So that's, you know, what we want to end up with as much as anything. But make sure we can do those. But and then x minus 5, x minus 5. So boom, boom, put in your 5 here. You get 12 over
0.
Did you do that right?
Yeah.
So it does not exist. So it started out, we started out getting 0 over 0, but we keep going, and then it turns out it still does not exist. Okay? All right. This one, put in a 2. We get 4 plus 10. 4 plus 14 plus 6 is 20. Oh, so we're just done.
Oh, yeah.
No factoring, no canceling. Now, did this factor? You did. The x plus 2 is canceled. You got x plus 3. Plug in a 2. You still get 5. You just did a little extra work. Right? So you can factor and cancel, but there was no need to. Okay? All right. Moving on. Now we get to the conjugate ones. So when you see this radical, that's where you want to do the conjugate. So you want to do radical x plus 3. Now, we've done a couple earlier. We did a couple where the radical was on top. And we had to do the radical, the conjugate on top or the bottom, doesn't matter. Probably what's happening is you get 0 over 0. So if these were flipped, right, you would still have 0 over 0. So you'd still want to do the same thing. It's where the radical is that you want to be looking. That's what you're trying to get rid of. So we want to, you know, you might say, well, the conjugate here would be 9 plus x. Yeah, but that's not going to make anything nice happen to make things cancel, okay? So it's radical x plus 3 that we want to do. So it's where the radical is we want to do this. All right, on top, I would leave that alone. We want to leave that part factored because we're trying to cancel. So that's why we want to leave it factored. Here we get what?
Minus 9.
Okay, so here's now a little algebra trick. We'd like to cancel those, can we?
Yes. Wait.
Sort of.
You can take a negative 1.
You have to take a negative 1 out. Now, I did hear somebody the other day when we were doing this radical thing was saying this, and when they did the conjugate was use the word opposite. Now, those aren't opposite, actually, right? They're not opposite. I mean, just think about 4 minus 3 and 4 plus 3. Those aren't opposites. One of them is 1, one of them is 7, right? They're not opposites. To make something opposite, you actually have to change the sign on both parts, right? So the opposite of 4 minus 3 is negative 4 plus 3. This one would be 1, this would be negative 1. So that's what we have to do here. When you've got a 9 minus x, this is the opposite of that. When you flip around a negative, that's when you get opposite. Think about 7 minus 4 is 3. 4 minus 7, negative 3. So flipping around a negative is opposite. So if I take a negative out of this, I would turn that into x minus 9, because the 9 would become negative and the x would become positive, which makes it this. So now I can cancel the x minus 9s. So I end up with a negative root x plus 3. On top, I don't have anything, or 1 on the bottom. Now I can put in my 9. Square root of 9 is 3. 3 plus 3 is 6. So I get negative 6. Yes?
What if you were stupid like me and tried to break it apart in the bow tie? Can you break
Oh,
it apart?
remember yesterday we talked about the only way to break apart a fraction is when you have a single denominator. So the only way this could break apart is if you kept it like this.
That's what I did.
You did that. Now that's okay, as long as you keep the denominator a single thing. But the only reason to bow tie is to get a common denominator. You already got one. So if you bow tie it, you'd be fine, but it would just get messy. It'd be really ugly. And then, I think if you did the right, I don't want to take the time right now, but I think if you did the correct algebra with all the ugliness, things would happen, it'd be okay, but I'm not sure anything would ever cancel.
Yeah.
You know what I mean? So I'm not sure you'd ever get anywhere. But I'd have to look at that and see. All right, so let's go over to this one. So now this one just looks a lot messier, but essentially what it is it's a radical minus a radical. So what you want to multiply by is a radical, same radical, plus a radical. And you want to do that here too. Okay, like so. Now the top you just want to leave alone. Right, you just want to leave that because we're hoping something cancels. And on the bottom, what happens when you FOIL this? First times first is just x squared plus 12. Outers inners would disappear. Root 12 times root 12 minus 12, which is a great thing because the 12s are going to just cancel. We're going to have the x squared down here that will cancel that. And so now you can put in your 0. 0 plus 12 is root 12. Root 12 plus root 12 is 2 root 12. Some of you are going to be bothered by that, and you'll want to make that into 4 root 3. That's okay, but you don't have to, okay, because root 12 would break into root 4 times root 3, which is 2 root 3 times 2. I don't care, either one of those would be okay with me. All right, number 7. Here, the thing in the parentheses we would bow tie. Now again, on these last couple I forgot to substitute right away, but I put a 0 in, you can see a problem right here, you got a 0. Put a 0 here, you're going to have 1/5 minus 1/5, which is 0. Now, what you get is 3 over 0 times 0. So that brings up an interesting question. We're going to talk about this more in a later chapter. But what does that mean?
0.
Well, it's not 0. It's 0 over 0. See, what people want to say is this is, we say this all the time, and it's not very precise language. We always say anything times 0 is 0. Well, that's actually not true. Not anything. Any number times 0 is 0. But is 3 over 0 a number? No, actually what it is a number getting really big. So what we have, if you really want to look, and this is what we're going to look at later, I'll just give you a little sneak preview. When we talk about x approaching 0, we're talking about x getting really small. Well, as x gets really small, that means this parenthesis is going to get really small, and this fraction is going to get really big, because the bottom's getting small. Now think about that. If you divide by a really, really small number, what happens? You get a big number. 3 divided by 1/millionth would be 3 million. Right? So what we have is a number getting really big times a number getting really small. So the answer to that is really which one wins? The one getting big or the one getting small? Well, guess what it's going to depend on? It's going to depend on how fast this one's getting big compared to how fast this one's getting small. It's going to depend on the rate of change. Oh, what's the rate of change? The derivative, rate of change. right? It's gonna depend on the derivative. Sneak peek. All right, anyway, do it this way. Think of it like this. It's 0 over 0. If you take 3 over 0 times 0, it's 0 over 0. So this means keep going. Keep going. So we're going to bow tie. So I'm going to take that times that, put that on top, 5 minus x. Take that times that, put that on top. Now I got a minus sign in between there, so I got to be careful, right? The bottom is going to be those together. So 5 plus x, 5 minus x. Then I've still got this 3 over x out in front, okay? Well, what do I get here? 5 minus x minus 5 minus x. 5's cancel. Negative 2x on top of 5 plus x, 5 minus x. And over here, I've still got the 3 over x. Now what? Now the x's cancel, which is what I wanted. I wanted x to approach 0. Now, that's not going to be a problem anymore. That was my 0 over 0. Those x's right there, now they're gone. And so now I can put in a 0. I got negative 6. Here I got 5. Here I got 5. 5 times 5 is 25. There we go. So bow tie, to get a common denominator. Simplify. Whenever you get that common denominator, then you simplify the numerator. Usually something's going to drop out, which is going to be good. And then you're going to be able to make something cancel. All right, this one's just about expanding this out. So the long way, 2 plus x times 2 plus x times 2 plus x. This actually has this look to it. I kind of snuck that one in on it.
Sure does.
Think about it. Instead of an h, I've got x's there, right? But you could think of the h's. Look where the h's are compared to where the x's are here. It's really one we've already done when we were doing derivative the long way earlier. So if I do Pascal's triangle, this would be 2 to the third plus 2 squared times x plus 2 to the first times x squared plus x cubed and then minus 8. Well, 2 cubed, those are going to cancel. So we're going to have 4x plus 2x squared plus x cubed all over x. I can take out an x. I'm going to get 4 plus 2x plus x squared. Did I do that right?
No, I think
You did it wrong.
Yeah, no. Oh, I forgot Pascal's triangle. Since I did the pattern and I said Pascal's triangle, I forgot it. I need the 1, I need the 3,
There we go.
I need the 3, and I need the 1. So 3 times 4 would be 12, and 3 times 2 would be 6. So this would be 12x, 6, okay. Right? And 1x cubed. Okay, now I take out my x, so that x will cancel that x. I put my 0 in for x, and I get 12. Right? 0, 0. I got the 12. Okay? Or you, like say, you just do 2 plus x times 2 plus x, get that answer. Take that times 2 plus x. Right? The 8's cancel. So that looks more like when we were doing the derivative ones. But I just wanted you to notice, remember I said yesterday the rectangle and square thing? Not all derivative problems are technically limits, because all derivative problems, that come from the definition, it involves a limit. But not all limit problems are derivatives. So 7 of these on this page had nothing to do with a derivative. They had nothing. They were just limit problems. Okay? What is the outputs approaching as x approaches this? But this last one, we work it the same way, and you didn't even have to notice that it had anything to do with that. But it does. It's a special limit. It's got to look like that, right? And so, but that's it. I mean, that's all there is to it. That would be the function x cubed, right? Because the 2 plus h, think of this as the 2 plus h, is where the x used to be. So the function is x cubed, and that would be the derivative at 2, right? Because that's 2 plus h, and that's the 2 cubed over there. So by doing this limit, this 12, what we really found was f prime of 2 for that function. And of course, with shortcuts, we know what is a derivative of x cubed. 3x squared. And if I put a 2 into that, 2 squared is 4. 4 times 3 is 12, right? So they match. But that's just a little extra there. But be able to do that limit. All right, so there's the algebra limit. So if we go back and look at what we talked about for the quiz. So, like that worksheet, be able to do some limits. That'd be on the no calculator part. Be able to do some of those algebraically. Maybe you plug in a number, just get an answer. Maybe you get 6 over 0, so it does not exist. If you get 0 over 0, you keep going using one of these methods. And maybe you still get 6 over 0, then it does not exist. But maybe you get a number, like we did on those last. Okay, so let's move along here. Let's talk about the calculator limit. So let's just finish up with this, and then maybe I'll give you a little bit of work time on that, and then we'll come back and we'll talk about the two, what this chart stuff looks like with some equating. So what do I mean by using tables? So just one more way I want us to be able to look at limits. So graphically, I want you to be able to see where the cars meet. Algebraically, I want you to be able to just go through some functions and be able to calculate the limits that way. And the last is with the calculator. So Reed is going to be up here. Let's do an example. Well, I tell you what, I'll just pass out the worksheet and we'll just do one right now. Right here. So, this part obviously would be on the calculator part of the quiz. Now this has two sides to it. We're just going to do the top side here, the side that says calculator limits. Really, I should, instead of calculator limits, I should say limits with a table. It is really what I mean by that. I really mean using a table. So you might write that at the top there in the directions especially. It says use your calculator. Well, calculators are so awesome. They'll just flat out do them. And that's actually the CAS part of this, right? The AP Stats calculators won't do this. But Reed, if you would go to the calculator side of this, and well, let's just do a real simple one here. Oh, interesting. I see what he was doing here. 3 over 0 divided by 0. Here it says undefined. Now, I don't like that language. I wish it would say, well, undefined's okay. But really, when we do limits, you'll see it says undefined also. And I really would say does not exist. We're not going to do any limits on this screen other than if you want to do them as a check, like when you're doing some homework. But it's really not going to help you on the quiz. But go to, let's see, I think it's under this right here, the catalog. Next to the 9, or the template's not the catalog. The catalog's the book next to it, where it's got all the different commands on the calculator. Which if you're really stuck, you go to that, but usually we don't need it. But this is the template key. And this has, notice there's a couple things this has in here. While we're here, we might as well mess with this a little bit. Go over to here. It's got Leibniz notation for the derivative. See that, the D, right? It's got the Leibniz notation. That's the derivative key. So when we talk about using the derivative key, we're talking about that guy right there. Hit enter, Reed. And then it brings that up. And then let's just do a real simple one here like we just did x cubed. So let's say we're going to do the derivative of x cubed. What would go right there? X. That's the with respect to. If we're going to do t cubed, we'd put a t there, right? If we're going to do x and then put x cubed in there. Or x squared. And we get, yeah, it's all right. Well, there it is, right? It did the derivative for us, right? It did it. That's really cool. Do it again. Do derivative again and put sine x in there this time. Okay? So, again, this is the CAS version of this. Some college professors are not going to want you to use a CAS on their tests anyway. They may let you on the homework. They may not let you on the test because they, for whatever reason, maybe they're just too lazy. Nope, that would go, an X would go down there. X would go down there. They might be too lazy. I shouldn't call them lazy, but they may not want to do a no calculator and a calculator part, right? They may not want to separate that out. So they don't want you to be able to do this and just do the derivative right there, right? So the calculator is going to be, when we're studying our derivative rules and we take our test on derivatives, obviously it'll be no calculator. But this can be a good way to check when you're studying to see if you're doing it right. Okay? All right, so go back to that template screen. So that's a derivative key. Go back to the template screen. Here's a limit command right down there. If you grab one of the calculators from the AP Stats people, these will be on there, but they'll be dimmed out, and you can't use them. So go ahead and hit enter. And now we can do, let's just do a simple one. So let's put X. And then in there we'll put, say, a 2. And notice the other little box, so we could put
Plus or minus.
I think,
It's a plus or minus.
maybe, okay, yeah, probably is, but let's don't put anything in there. Yeah, plus or minus from right or left. And then let's just do like x plus 3. Just something real simple. Hit enter, and we should get 5, right? And sure enough, it doesn't, right? So all these limits on this page, we could type into there and get the answer as a check. It is pretty nuts, okay? But you guys are kind of like third graders learning your multiplication tables, and I'm not going to let you use the calculator to do that, right? Just like your third grade teacher when you're learning your multiplication tables. But it may come in handy. There'll be times where it'll come in handy where you might check some answers or whatever. So that'll be good from that standpoint. So when I say use a calculator, what I really mean is use the table function on your calculator. So we're going to go to our graph. So the very first one here, well, heck, let's make one up first. So go into your graph screen. So hit your scratch pad button again here. There you go. And let's hit the tab key and get our y equals up there. And let's get that out of there. And let's put in 1. Do your fraction. Oops. Do your fraction key. And let's put x squared minus 9 over x minus 3. And we want to investigate this. Where do you suppose we want to investigate this? As x approaches what? 3. That would be the point of interest, right? At 3. Because if we put a 3 in there, we're going to get 0 over 0. Okay, so let's go ahead and graph that. Let's go to a window. Let's do a standard window. Hit escape because you're in the trace mode right now. And maybe you meant to be. Go to window, zoom, and let's do 5, zoom standard. Okay, there we go. And he went ahead and, well, he's got those other points there, but I'm not sure. I think there's a quick way to get rid of them, but I can't think of it right now. Can you grab it maybe or click on it, hit delete? Yeah, there you go. He's better at this calculator. There you go. So you click on it and then it's kind of clicked and highlighted. Okay. So let's trace. So let's go ahead and trace at 3. And what should we get when he traces at 3?
0.
No? It's undefined, right? It's 0 divided by 0. We already knew that, right? We put a 3 into there, we get 0 divided by 0. There's a hole there. There's a hole there in the graph at 3. But what is the limit? Can you do the algebra in your head?
X plus 3 is 6.
It'd be 6, wouldn't it? Because it'd be x plus 3, x minus 3. The x minus 3 is a cancel. It'd be x plus 3, plug a 3, and 3 plus 3 is 6. So algebraically, we know this is going to be 6. But I'm going to give you some more complicated ones in this, since you have your calculator. What I want you to go to right now is the table feature. So if you go to menu, and you go down to table, and you go to split screen table. Now, you can also get that by, right now, I think if you hit Control T, I think. Try Control T. It went away. And Control T will bring it back. So I think whenever you're in the graph screen, if you hit Control T, you can bring in your table. Okay? And so let's put in, and here's what we want to do. What I want to do is it's kind of like the spreadsheet the other day. I want to look at the table, and I want to look at x values really close to 3. And I want to see what the y values are. Now think about that. Isn't that what the limit is? The limit is what are the y values approaching as the x values are approaching 3. So on my table, I want to see x values really close to 3, and I want to see what the y values are. That should tell me the limit too. So what I want to do is I want to go in here, now that we're in the table, see how the table is highlighted? You can do that by clicking in there or whatever. Now go to menu, and your menu options are different now than they are on the graph. See that? So the menu options are now different. So go down to table, and right arrow, and let's go to edit table settings. Okay? And what I want to do is I want to start my table at 3. Because we're interested in what's happening when x is 3. And what do you suppose table step I want that to be? So how much do you think, what do you think I want to put in? 0.001, I would say. Right? Because I want to see when x is getting really close to 3, I want to see what the y's are doing. Right? So I'm going to put like 0.001. That's probably good enough. And those other two you can leave as odd. So go ahead and hit enter. Now, notice what I get right there. Now, we knew the answer was 6, right? Now, I want you to do one more thing before we're done here. I want Reed to arrow up a couple, because I want 3 to be in the middle of this table. So arrow up again, and arrow, well, that's probably either way. Can't quite see as much as I'd like to on the table. Okay? Now, do you see how there's no value here for 3? Do we care? The diner burned down, right? The diner's not there. We don't care what's going on at 3. What we care is what these Y values are doing, right? Do you see how that's the cars coming in? And the Y values seem to be approaching what? 6. And of course that was our answer, was 6, right? So I'm going to ask you something. So on our worksheet here, we're going to do this. And on the quiz, there's going to be somewhere I'm going to say, one way or another, give you a limit, or maybe will be a derivative problem like this. I'll tell you to set up the limit. And then I'll tell you to go to your calculator and put that in and look at it. And then here's your answer to this. You would write on your paper, you would write this table. And I'd want 5 rows of the table. I'd want 3 in the middle. I want a couple of values under 3, and I want a couple of values over 3. And I wanted the X and the Y values. And that right there just shows me, oh yeah, the answer's 6. Matter of fact, I might even give you this problem. I might even say the limit as X approaches 3 of this function equals 6, and then the directions will be justify or prove this limit is true by a table. You know what I mean? I might just give you the answer, right? Because I don't care about the answer. I know you have your calculator. You can just type in. I want you to show me the justification of why it's 6, right? And this table does it, so you just copy it out the table. Okay, so let's go to the first one on the worksheet. Okay, let's go to the first one on the worksheet. So go hit, you can hit Control T if you want, or just click over here into your graph, actually, if you want to. Just leave the table up there, heck. And then just click over your graph and hit the Tab key to bring up the Y equals. You can just leave the table over there. And let's delete that guy out of there. And let's put this first one in. Okay, so go ahead and no.
Don't put that in.
Yeah, no. I'm sorry. What we want to do, just hit delete. There you go. We just want to put that function that we're doing the limit, right? So what we're trying to do is we're trying to do the function that we're doing the limit of, right? And we want to see what those Y values are approaching as the X values are approaching 0. So all we want to do is put in the function here, right? And we want to see the Y values of that function. So we're doing the limit ourselves, so we're not going to type in the word limit. And then we want to see as X approaches what? So how do I do that? Yeah, I got to click over here on my table. See, because right now we're doing X approaches 3, right? Right now we're doing X approaches 3. So that's no good. So we're going to go to our table settings, right? We want to click on our table so it's highlighted. We'll go to Menu, Table Settings. Now we want to start our table at 0, and I think 0.001 is pretty good. I think that gives us a pretty reasonable number. And then hit OK. And then you probably have to arrow up a couple. So we want 0 to be in the middle. So usually 0 is going to be undefined. So what does it look like? Move your cursor up there a little bit, Reed. Or why is it, or click somewhere? Point. So it looks to me like it's coming in at about 0.5, right? What would your table look like if it does not exist?
You would have like two numbers below, like a higher point.
So this might be coming in really close to, say, 0.5, and these might be negative 0.5, for example. So these are negative, so these would be X's to the left would be coming in at 0.5, and the right would be coming in at negative 0.5. So that would be it does not exist. The cars would not meet. Or sometimes you get really big numbers here, like that E, that like 10 to the 12th or 10 to the 15th or something. Well, what that means is like it's an asymptote, right? So if you get values here that are these really big numbers with scientific notation, it means from the left it's going up, and then down here a lot of times they're negative, it's going down. So the cars would meet. Or even if they're both going up, the cars aren't ever going to meet, right? So we would say does not exist. So that's what a table would look like if it doesn't exist, is these would not be coming in towards the same number. So now jot that table down. Just jot that table down is how you do your worksheet. Okay? I'll give you, I tell you what, you guys on your own do the next one. Go ahead and jot that table down. On your own, do the next one. Now, I need to leave myself enough time to do one more example, an example problem here. So, probably give you enough time to do one more on your worksheet here. So you just go into your function, you change it to the new function you're doing. And again, now a lot of these are x approaches 0. So a lot of these, I should have varied it a little bit, to be honest, as I look at it. But, so a lot of these are x approaches 0. So you won't have to change your table much. But then I throw in, once or twice there, I throw in like x approaches 3 or x approaches 2. You got to catch that. You got to make sure you adjust your table. Because the middle of the table here has to be what x is approaching. Let's go ahead and move aside from that then, and we'll do one last type of problem here that I want to look at, just getting a little bit of a start in section 4. Now, I've left off a few things in section 3. We're going to come back to those tomorrow. There's a variety of things going on here. And so, we want to make sure we get to hit each of these things a few times. And so, that's kind of why it feels a little bit like we're jumping around. Notice I said we were taking a side trip a little bit in talking about limits. Because in yesterday's homework and most of today, we've hardly mentioned the word derivative. You know, every once in a while we've referenced that over there, but just because it is a limit, right? And so we've been talking about limits and what they are and the different ways we can find limits. But now we want to draw our attention back to this idea of a derivative a little bit, and kind of the final thing that I said was going to be on the quiz is the chart stuff using equations. So this is number 19 in the book. You're going to have for your homework number 21, which is very similar to this. So this would be a good resource. So I would copy this down, and so tomorrow when I come around and look at homework, I'm going to look at number 21, and I'm going to want to see if it looks like this. Because the answers to 21 are very easy. You can just write it down. You can look at the back, you can just write down the answers. But you're going to have the work shown that we're going to do here. So the work you see here, you're going to want to kind of mimic that when you do number 21 in tomorrow's homework. Okay? All right. So we've got this function. It's a cubic function. This would be a no calculator situation. It's a cubic function. We know those kind of go up and down and maybe up again, or maybe it just goes and flattens, whatever. So there's a very much a possibility of a local max, a local min, that kind of stuff. Where is that at? Okay? Well, think of the chart. Where do you look for a local max or min on F? Yeah, when F prime changes from positive to negative, which again, where do we, if I give you an F prime graph, where do you look right away? When F prime is 0, local max and mins, first entry in the table, right? F has local max, mins, or flat spots when F prime is 0. That's what we care about. It's the very first entry in the table, when F prime is 0. So what we want to do is find out when F prime is 0. Graphically, that was easy. If you had an F prime graph, you just look across the x-axis. With the equation, it takes a little more work. Do we know what F prime is? What is it?
3x squared minus 6x.
What's the derivative of 5? 0. Right? 5 is just a constant. Derivative is 0. So that's F prime right there. Our handy dandy power rule, right? It's great. And we want to know where that is 0. So we just set it equal to 0. And we solve. How do we solve that? And a 3. You wouldn't have to factor out the 3, but you could. Factor out of 3x, we get x minus 2. So either x is, I usually write next to that SP for stationary point. Isn't that what we just found? We found the stationary point. Now, if you wanted to graph this x cubed graph, it's going to go up, hit 0, keep going up, come back down at 2. No, wait. Let's see. This is f prime graph, I'm sorry. But which would be really helpful, right? If you wanted to graph this is a parabola, which actually goes up, so I had it backwards. It's going to go down, hit 0, come back up through 2. And if, now, I wouldn't normally do this. I'll go ahead and write it off to the side here, because normally our functions are going to be complicated enough that maybe you're not going to know the graph that easily. But man, this could certainly be helpful, that if you knew this is going to be a parabola, it's going to hit at 0, go down like this. Because of the work we did in chapter 1, don't we know about everything we need now? Positive, negative, positive. Aren't we going to have a local max at 0? Positive to negative, local min here. Okay, but let's pretend we didn't do that, okay? Because many times we're going to get f primes that aren't just easy parabolas or something like that, right? And it's not going to be as easy. Or they're going to be trig equations, or they're going to be e to the x or something. So here's what we'll do instead. We're going to do what I call an f prime number line. This is going to be a really important thing for you to use as we go forward. So everybody jot this down. So what you want to do is you want to take your 0 and your 2 and you want to put those on a number line, like so. And I labeled it. Notice I labeled it f prime, because later we're going to get into inflection points, which involves f double prime. So we're going to have a number line for f double prime too. So you want to make sure and label this properly. Okay? So I'm making a number line. Now what do I really care about? What was so interesting to me on my f prime graph? It's where f prime was positive and then negative and then positive, right? Well, I can get that same information by just plugging numbers into f prime, right? I don't need the graph to tell what the y values are. I can just plug in to f prime to get the y values, right? So now I'm not going to plug in a 0 or 2 into f prime, because what will I get? Not just get 0. I mean, those were my stationary points. But what I want to do is I want to check on each side of those. So I want to check a number. So I'm going to write them a lot smaller, but I want to check a number like -1, and maybe 1, and maybe 3, right? I want to find some numbers that are in between here, and I want to plug those into f prime. Think about this now. Because won't that tell me if f prime is positive or negative? Right? Makes sense? So, and I don't have to check anywhere else, because I know these are the only 2 places where f prime is 0. So I know it'll never change any other places, right? Because the only way the graph can change from positive to negative is to go through 0. Right? Unless it jumped and had a break, which this will not. All right. So we put a -1 in here. Now you can go back to the original if you want, but this one is probably the best one to work with right there. Right? So let's plug in a -1. So 3 times -1 is negative. -1 minus 2, negative. I don't even care what it is, really, do I? I only really care if it's negative or positive, right? So negative times negative. So I know I'm going to get a positive value over there. See what's happening here? I'm going to get the same information from this number line that we've been getting from our f prime graph before. Let's put a 1 in. 3 times 1 is 3, which is positive. 1 take away 2, negative. Positive times negative is negative. Now I'll put a 3 in. 3 times 3 is positive. 3 minus 2 is positive. Positive times positive. Now what would happen if you made this number line and all of a sudden it went positive, negative, negative? Flat spot. Isn't that a flat spot? It's a flat spot. Because think about this. Think of the chart now. And we've been away from it for a while, right? But f prime's positive, negative, positive means f is up, then down, then up. Well, if you had negative, negative, it'd be up, down, and keep going down. Well, it's a flat spot, because we know this is where the derivative is 0, so we know it has to be either local max min or flat spot. Right? Okay. So with this number line alone, We know everything we want. Now, number 19, it asks you 4 questions. It asks you, where is F increasing? So it'd be negative infinity to 0, 2 to infinity. See how these are the same questions we were doing last quiz, right? Using the chart, same kind of thing. Where is F decreasing? From 0 to 2. Where is their local max? At x equals 0. Local min? X equals 2. Now, what I haven't put in there was justifying your answers. It is not enough. The AP test, they're very clear. When they grade the AP test, they will not even look at this. This, I'm going to have you do it because I think it's very helpful information. But if they ask you to justify your answer on these, this is not a justification. You've got to say, well, F's increasing here because F prime's positive. F's decreasing here because F prime's negative. Why is this a local max? You actually have to say, that's a local max because F prime does what? Switches from positive to negative. Therefore, F switches increasing to decreasing. You've got to make that F prime and F connection. So if they say to justify it's a local max, you have to say F prime changes from positive to negative, so therefore F changes from increasing to decreasing. You got to make that connection. Now the other one, they say F's increasing, you say because F prime's positive. You already made that connection, right? Because they F, and then you said F prime. And local minimum would be the reverse. F prime changes from negative to positive, so F changes from decreasing to decreasing. Okay? So you would have to add that into your explanation if they ask you to justify. And with local max min, they almost always do ask you to justify. So tomorrow when you do 21, I want it to look like that. I want to see F prime set equal to 0. I want to see a number line, right? And then your answers to that question. All right. One last thing, and it's just a notational thing. So we got our chart here. I should just pull up the chart. Let me pull up my chart here. The chart. Now, notice in this chart, I do not have any F's and G's and stuff over here. Why is that? Couldn't I make this line be F double prime, and then what would this line be? You know, whatever, right? We don't typically get into that, but I could, right? I could. So normally we think of this chart as over here as this line is F, and this line is F prime, and this line is F double prime, normally. Okay? Now, we're going to talk tomorrow about something called the antiderivative. The antiderivative. Now, this is not going to be a big deal on this next quiz. It will be on the one after that. Here's all it is. Listen, here's all it is. If we go down, we're doing the derivative. So if we go from F and we say do the derivative of F, that's F prime. And do the derivative of F prime, that's F double prime. The antiderivative is just going the other way. F is the antiderivative of F prime, and F prime is the antiderivative of F double prime. That's all it is. That's all it is. Okay? Now, so the question then becomes, what if you started with little f, hint, hint, and you wanted to do the antiderivative of it?
Of F?
Of f. Because it doesn't make sense. I mean, think about it. If I had x cubed, I could do the derivative of that. That'd be f prime, right?
Right.
But couldn't I have, and that would be 3x squared, right? But what if I called 3x squared f? What would be the antiderivative of 3x squared?
Slope of
Well, no, but I mean, what function would it be? I just said if we did x cubed and did the derivative, that'd be 3x squared, so f and f prime. But let's say I called 3x squared f. What's its antiderivative? F, would it be x cubed, right? I mean, so it's just a naming thing. So my point is, if you've got a function f, doesn't it have an antiderivative? Isn't there some function that if you did the derivative of it would give you f, right? So really the question I'm asking is not what does it mean or represent. Some of you are saying slope, and that's good. I get where you're going with that. All I'm after right now, though, is a name. What are we going to call it? Right? I mean, because we got f and f prime and f double prime. Well, here's what we're going to call it. We're going to call it big F.
What?
Now, you might say, what happens if you do the antiderivative of that? Bigger F? No, we won't do that. We won't talk about the second antiderivative necessarily, whatever, okay? So we won't have to worry about that. But here's why I bring it up. Well, number one, you're going to have some homework questions about it. But number two, I noticed some of you on the last test, when we were doing F questions, and it was little f always in the questions, but when you were writing F, you were writing what looked like a capital F. So now you've got to be careful of that. Because we now know that little f and big F are two different things. Okay? So, what that means, now think of this now. What that means is my chart could now look like this. This could be big F, and then this one would be big F prime, but we've just said that big F prime is the same thing as little f. And big F double prime then is the same as little f prime, right? So, I know, but trust me, it'll be fine, you'll live through it, okay? But big F is the antiderivative of f. That just means if you do the derivative of big F, you get little f. And then you can just go through the thing. So, on your homework, so go ahead and grab your homework sheet.
So the derivative of big F is F.
The derivative of big F is little f, and then the derivative of that is f prime.
Which is the same thing as
Big F prime. Big F prime is the same as little f.
Write this down.
Big F prime is the same as little f. All right. So, let's put it all together here so we understand what our homework is. So if you look at the next couple of lines there on the homework sheet, it says you've got 2.4, so make sure you go to the right page when you do your homework here. 2.4, 3 through 12. Now, that seems like a lot of problems, but it's really not. Here's what it is. They give you a graph. It's really questions like you did on the last quiz. Except the differences are going to use big F. So they're just going to get you used to that notation. Now, I can't remember if they give you a big F graph and ask you questions about little f, or it might be they give you a little f graph and they ask you questions about big F. Now, isn't that the same thing we did last chapter? Last chapter, you did this. I gave you an F prime graph and asked you questions about F a lot. Well, now they're going to give you a little f graph and ask you questions about big F. Same thing. It's the same thing. So you're going to have those questions that are going to be very similar. The only difference is using this new notation, big F. All right. Then you got number 21, which we just talked about. Needs to look a lot like number 19. Okay, you're going to do a number line, that kind of thing. So I give you practice at that, and then finish this worksheet with the calculator there. Just the one side, not the back side. Don't do the back side. No, I don't want to kill you.
You already did.
Oh, I did?
This
The big F thing?
So is that actually called big F, or does that have a name?
No, a capital F, maybe. I always call it big F, but no, it's the antiderivative. But it's just notation. It's kind of accepted
It's getting
notation.
us to like
So
big
like,
F.
what does big F like look like?
Well, it's just a name. I mean,
Yeah, what
If
does
it's
it look like?
F, it's a,
Yeah, what would the
miles
graph look like?
per hour.
say that again.
What would the
Well,
graph
what
of
is
big
it?
F look like in function?
Like if F is miles per hour or so, like what is big F?
If F is miles
And then-
per hour,
Well,
or just miles.
Just
Miles.
miles then
an hour.
hours.
Time is out.
Not the X.
Hours.
The X axis.
Yeah, like that.
What is,
Would be big F.
Well, I'll tell you, here's how you could easily answer it. Okay, right? Wouldn't this be the order? Big F, the derivative of that is this.
Yeah.
The derivative of that is this,
Yeah.
right? So tell me what the units are in F prime here.
Miles per hour. Per hour.
Miles per hour, and then this would be hours, right?
Yeah.
So tell me how we went from this one to this one. How did these units turn into those units there? No. Wouldn't it be these multiply? Well, think about it. How did we get miles per hour? We divided the y and the x's. So if you go the other way, what do you think you do? You multiply. So what would be the big F units?
Miles times.
Mile hours?
Times hours.
Mile hours? Which is a meaningless unit, so you would never have that in a problem. But if you know anything about electricity, you hear of kilowatt hours? Kilowatt hours is a meaningful unit in electricity. So you could see something like that where you would multiply those units. But you're right, what you would more likely get is you would get an F, little f, that would be miles per hour. And so therefore big F would be just miles. Right. Because, and that's one of the reasons we don't keep doing like third and fourth derivatives, because at some point the units really are meaningless. They don't really have, in real life setting anyway, they don't really have a base or yeah. But yeah, because miles hours wouldn't really mean anything, so.
Because Matt?
I know, right?
Hey, Clay. If I was to do a satire paper, and I'm going to write about peanuts. What? We're going to write a satire paper, I'm going to be very sarcastic and write about peanuts. I'm going to try and sound like you. What? My goal. Clay, I'm going to try and accomplish your voice. Hold on.
Yes. No, right undefined, yeah, good question. Hey, you guys, listen, hey, on that worksheet, when you copy down the table, in that middle entry, like by 0 or 3 or whatever, I want you to write out undefined.
Yeah.
Actually put undefined in there, yeah, not what it's approaching. Now, it's possible that you might get one that has a value in there, right? Because sometimes the cars meet and the diner's there. There is a value, so it might not always be undefined.